Okay, welcome. Remember, it takes all kinds to make up a world. Today we are going to look at a little bit more of advanced nomenclature for organic compounds. So we're going to go past the alkanes, alkenes, and alkynes. And specifically, we're going to look at something known as functional groups. And you can look at this cartoon if you want later on and see how it's talking about dysfunctional groups. But organic functional groups, this is pretty trim as far as what you guys need to know. All you're going to need to be able to do really is recognize those functional groups, and you need to be able to do that from either the name that is given or the structure that is drawn. So again, all you're going to have to do is be able to recognize and list what that functional group is. You will not be expected to actually name or draw the compound. So I just want to make sure that that's clear. Okay, so the first one that we come across, you guys have already seen this when we just briefly touched on, I think, actually I don't remember if we had it in the notes or not, but it would have been very brief if it was. They're known as aromatic hydrocarbons, and they contain a closed ring structure. So this is a little bit different. They're not cycloalkanes, alkenes, alkynes. They are known as aromatic hydrocarbons. So they have a closed ring structure and they have alternating double and single bonds. A couple different ways you can represent that. You can represent it with a structure such as this one right here, and this is a little hard to see, but you've got those alternating double and single bonds in there. So that's one way to do it. Or it can be represented with, of course, the hydrogens. Or these two structures are saying the same thing. Both of these, this happens to be the simplest aromatic, and it happens to be benzene. I do want you to know benzene. You should know that one because that's the simplest aromatic hydrocarbon, and it really is one of the base structures that is used in a lot of the other aromatics. So that one you should be able to identify, possibly even draw. The others that we have here, just notice if you saw a diagram of one of those guys, you would be able to look at that and say, yeah, that's going to be an aromatic hydrocarbon. Now, when we start thinking about the polarity of this molecule, notice that it is the same all the way around. And we're not really talking too much about these little substituent groups. I know we're leaving that out of this unit, but for the most part, let's just say when you look at one of these structures, it looks the same all the way around. So there are no poles on it, no positives and negatives. So if it is a nonpolar compound, remember you've learned that what that means, the intermolecular force that's present, the only intermolecular force that is present, is going to be London dispersion forces. So very weak intermolecular forces holding those compounds together or next to one another. Okay, so our next functional group that we want to look at is something known as alcohols. And what you should notice by this is that they are characterized by the functional group of an OH. It's known as a hydroxyl group, And the way this is named, whenever you name that alkane that you might notice, for example, I would look at this here and see I have 1, 2, 3 carbons, and of course they started numbering from the opposite direction because they're going to start where this OH is. But that's not important. We're not going to go into all of that. Just notice that there's 3 carbons, so that's why they named it with the prop and the ane. Instead of the E on the ending, though, it's an OL, so propanol is how that is named. Um, Again, all you need to be able to do is look at this either from the structure and notice that there's a hydroxyl group on there, or look at it from the name and notice that there's an OL there. That is all that is expected of you. So because of that, you would look at either one of those and say, yeah, that has got to be an alcohol. If we were to look at some of our I guess the polarity here, we notice that in this drawing, in any of these drawings, because of that OH, you do have a polar molecule. You've got an extra share of those electrons right in here with that oxygen. So you've got more of a polar molecule going on. It's very polar, in fact. Because of that, And because it's polar with these two elements bonded together, that makes it be a very strong, strongly polar molecule, and our IMF that is present is going to be hydrogen bonding. So remember that your hydrogen bonding is going to be when you have hydrogen bonded with nitrogen, oxygen, or fluorine, one of those. And we see that going on right here where oxygen and hydrogen are bonded together. So because of that, you're going to have hydrogen bonding, which is very strong dipole-dipole force. So you've got a very strong IMF, and it's a very polar molecule. Okay, then we get to our ethers. Again, we're looking at organic compounds. And for this, in this situation, we've got an oxygen that is in between, somewhere in between your carbons in that chain of carbon. There's a couple different ways that you might see them. Again, you just have to be able to recognize them. They're either symmetric or asymmetric, and it just depends on where that oxygen is. So there's a couple different ways. Well, the way we're going to name this is we're going to see the word ether in there, and then the substituent groups, however many of your carbons that you have on each end, that's going to be what is used up front. But do not worry about this beginning part. You just need to be able to recognize it from either the name, so that's pretty much a no-brainer. If you were to see those names, you would recognize that that's an ether. Or you need to be able to recognize it from seeing the structure. So as far as seeing the structure goes, you see these carbons, and somewhere in the middle, you've got that oxygen that's bonded in there. So when we used to get a little bit more involved in the naming of these functional groups, we would refer to this as being the ether bunny. There's his ears and his little face. So you've got your oxygen somewhere in the middle of two little groups of carbon atoms, a chain. And if we're looking at our polarity here, again, we're going to have a nonpolar molecule for the most part because this oxygen's somewhere in the middle. So because of that, it is not going to, two different sides of that molecule are not going to have a strong positive or negative side to it. Also notice that, I know it's kind of deceptive sometimes when you see something like this in a condensed structural formula, but if we were to draw this as a structural formula, I would see that I have two carbons, an oxygen, then a carbon. Here are my three hydrogens. Here are my two hydrogens. Here I've got three hydrogens over here. Now notice that this oxygen, all that's going to happen is he's got lone pairs in there. So that oxygen is not bonded to a hydrogen. Therefore, there is no hydrogen bonding going on. That oxygen is bonded to the carbons. As is the case with all of these, you've got hydrogens bonded to carbons. That does not imply any hydrogen bonding. Hydrogen has to be bonded to nitrogen, oxygen, or fluorine in order for there to be hydrogen bonding going on. So no hydrogen bonding in this case. It is a nonpolar molecule. So our only IMF that's present is London dispersion forces. Then we move into our aldehydes. Aldehydes, you have, let's see what's better to look at. Let's just look at this guy right here. You have a carbon, and notice that it is a, somewhere it tells us it's a terminal carbon. I don't see where that says that. The E, it should tell us somewhere, maybe we took those out of the notes and we need to add this back in, so this is huge, that this double bonded oxygen is on the terminal carbon. That's huge. You need to write that down. I need to make sure I get that back in the notes. We were amending things and I think I took that out by mistake. So double bonded oxygen is on that terminal carbon, meaning it's always on that tail end, or it really could be the front end as well. We use the word terminal. It's when naming it, if you happen to be pretty observant, you might notice that it's always, we count this as our first carbon is what we're always going to do, and this is our second, third, etc. But it's considered on that terminal carbon, you've got a double bonded oxygen. So because you have this double bonded oxygen here, of course you've got a bond going over here to another carbon, so you have to have this bond here to that hydrogen. That's always what it's going to look like. So that functional group we think of as looking just like this. The C with a double bonded oxygen and a hydrogen right there. And then the rest of this goes off to the chain, this reaction chain. That's what that R stands for. So you've got different carbons, etc., that are going to be attached there. When you name these, the base name is going to be from your longest continuous chain. So again, I'm not going to ask you to do that, but you can probably look at this and say 1, 2, 3, 4, 5. There's 5 carbons. Instead of it being pentane, it's now a pentanal. That's the ending that we need to know about. When you see an al ending, al, that implies that it's an aldehyde. Notice that it sounds pretty similar to an alcohol, but it's an aldehyde, so be careful about that. The IMF that's present is a dipole-dipole force because, again, we do have a polar molecule. In this case, you see it's always going to be on one end. You always end up seeing that you've got this oxygen here on one end of your molecule, which has a much greater share of those electrons. Therefore, it's going to be more negatively charged. But that oxygen is not bonded to hydrogen. Therefore, there are no hydrogen bonds. It's only a dipole-dipole force, which makes it's a polar molecule. Okay, ketones. Very similar. You've got a double bonded oxygen to a carbon, but it is not on a terminal carbon. So it is always going to be somewhere in the middle. Ketones are recognized again by this double bonded oxygen to your carbon. And then on each side, you're going to have your reaction chain. When you name these, you're just going to change your E to an own at the end. So it's going to have that own sound to it. And let's see what we've got here. There is another way that we can recognize it that has the word ketone in it, which is pretty straightforward. But if you look here, you see you have a carbon and a double bonded oxygen. That's how you identify your ketone. Again, carbon, double bonded oxygen, carbon, double bonded oxygen. Notice in the second example, this middle one, that double bonded oxygen is not on that terminal carbon. It's not there on any of them, but if it were, that would be a completely different substance. So ketones cannot be on a terminal carbon. In the naming of it, we have just changed our hexane, got rid of the E, and made it a hexanone. So pentanone. And then this is the alternate naming system. We have some sort of ketone. So you should be able to identify this functional group from either the structural drawing or from the name. And again, much greater share of the electrons with this guy. So it's going to be a polar molecule, which means our IMF that's present is dipole-dipole. Okay, carboxylic acids. In this case, again, we have a double bonded oxygen, but notice we've also got another oxygen in there. And this is always going to be, I'm afraid I dropped it on this one as well, always, let me say, oxygen, always double bonded to terminal carbon. And again, on top of that, you've got a hydroxyl group really right there. So that is the big difference that we see with this one. So your oxygen is always double bonded to the terminal carbon. That was left out of your notes by accident. Maybe I'll get that in there before you guys actually get a copy of your notes. If you were to look at the structure, you see your terminal carbon, double bonded oxygen, and an OH. Terminal carbon, double bonded oxygen, and an OH. So when I look at that structure, I can definitely identify that as carboxylic acid. When I look at the name for this, we drop the E from your alkane and you add oic acid. So in this case, instead you've got this 6 carbons, 1, 2, 3, 4, 5, 6. You have that hexane, but you drop the E and it becomes hexanoic acid. So that is a carboxylic acid. You can have something like this with an alkene or an alkyne as well. It's kind of hard to see, but there's a double bond in there, so that's why that naming occurs. But it's still a carboxylic acid. Because you have this hydroxyl group right there, just like with the alcohols, you've got hydrogen bonded to oxygen. That is a really strong dipole-dipole force. So that's going to be a hydrogen bonding that we have going on. That makes for a very polar molecule when you have a very electronegative element bonded to hydrogen like that. And our last one, I believe, our last one are esters. And these are derived from, the names of these are derived from both an acid and an alcohol. And what you're going to see here, again, you've got that double bonded oxygen to a carbon and another oxygen next to it. That should look kind of familiar. That's almost what we saw here. But notice it's not on a terminal ending there. Instead, it's somewhere in the middle, and you don't have that hydroxyl group. It's just a double bonded oxygen to your carbon with an oxygen next to it. So the way that these are, I guess from your drawing, again, carbon with double bonded oxygen and another oxygen somewhere in the middle, so that's how you can identify them. And then from the name, you're going to notice that we've got this substituent group. In other words, it's your alcohol is you have a substituent group that has a YL ending, and then the acid chain changes to an O8 ending. If you didn't quite follow that, that's okay. But really what you're going to have is some sort of what's known as a substituent group. It sounds it's got the same prefixes, but you've got that YL and then something else, another prefix with an O8 ending. So ethyl, ethanoate, methyl, propanoate, those are going to be esters. You should be able to identify those names as esters. And then finally, we can say something about our IMF that's present. Again, we know it's a polar molecule because we have this double bonded oxygen getting a greater share of those electrons. But notice your oxygens. Your oxygens are always bonded to carbon. They are not bonded to hydrogen. So because of that, it is merely a dipole-dipole force. It's a polar molecule that is dipole-dipole. It is not hydrogen bonded. I am not going to fill this in, but I put this on your notes just thinking that you might want a space that you can go ahead and kind of summarize this for your studying purposes. So you can go ahead and write in your functional group, the name of it, and then also you might want to go ahead and say something about your IMF or polarity or something for your studying purposes. All right, so now we can look at some examples of how to identify functional groups. And all of these, none of these are where you're given names. All of these are where you're given structures, because I think that's a little bit more challenging. In this first example, what I would identify, and I'm going to go through this pretty quickly. Actually, maybe a good way for you to do this is for you to try to identifying these functional groups and then just checking yourself. So feel free to pause this if you'd like. This first one, I look and I see the OH, that hydroxyl, so I know that it's going to be an alcohol. And then down here, same sort of thing. I see that OH, which is my hydroxyl, so it's going to be an alcohol. Over here, looks like we've got the ether bunny going on, so there's an ether. This one, same deal, we've got an O right there. So again, a little lopsided with his ears, but we have an ether. And then here we have our alternating double and single bonds, 6 carbons, so we know that that's going to be an aromatic. All right, so here's our aromatic hydrocarbon. Now, on some of these things, you're going to notice some additional things like your bromines that are attached to it. Yeah, you happen to have some alkyl halides that are also attached, but that doesn't have anything to do with this, so don't worry about that. Doesn't change the name. All right, next one, I look and I see again that hydroxyl group, so I know that I have an alcohol. And here I've got a double bonded oxygen, and with that double bonded oxygen, it's on a terminal carbon, so that's got to be an aldehyde. Here I have a double bonded oxygen as well, but it's not on a terminal carbon, so that's got to be a ketone. Again, double bonded, not on a terminal, so it's going to be a ketone. Now in this case, I've got that double bonded oxygen to a carbon that's somewhere in the middle, but I also have another oxygen in there. So that one's a little bit different. That's going to be our ester. And we see the same thing here, just happens to be going to the opposite side. Again, that's going to be an ester. Now in this one right here, double bonded oxygen on a terminal carbon, but we've also got a hydroxyl group, so that has got to be a carboxylic acid. Okay, remember that there's different ways to show aromatic hydrocarbons. This just happens to be a different way of showing that double and single bond with our 6 carbons. And again, that's going to be aromatic hydrocarbon. Over here, double bonded oxygen on the terminal carbon. There's an aldehyde. So here we've got a double bonded oxygen with another oxygen within that chain, so it's going to be an ester. All right, here we've got our double bonded oxygen to a carbon with nothing else in there, so that's going to have to be a ketone. What do we have here? I see a hydroxyl group, a bunch of these other substituent groups, but that looks like that's just going to be an alcohol. Double bonded oxygen to a middle carbon and another oxygen in there, so there's what we've got is an ester. Same sort of deal over here, double bonded oxygen with another oxygen over here. It's not on that central carbon, or that terminal carbon, it's on a middle one, so that's going to be an ester as well. I'm going to go down to this one because this one's pretty easy. This is just an alcohol. Now, this is probably our most challenging one that we have. Remember, we're looking at a condensed structural feature, or condensed structural diagram. So what happens here is we're not necessarily seeing exactly what goes on. There are my 4 carbons, there are my 3 hydrogens, 2 hydrogens, 2 hydrogens. Now what's going on here is we actually have a double bonded oxygen and a hydrogen. If you saw it like that, I think that would be a lot more obvious for you, that that has got to be an aldehyde. But when you look at it in the condensed structural formula, I think what should catch your eye the most is that you don't see an OH, but typically it's written as an HO. So that's not an alcohol, that is an aldehyde. And here, double bonded oxygen, same sort of deal where you've got that condensed formula. So double bonded oxygen and then an OH, and it's on a terminal carbon, so there's our carboxylic acid. What do we have? Right here we've got just an alcohol. And where am I? Let's go down here. Same sort of deal. You've got that carbon. You've got carbon with a double bonded oxygen and a hydrogen, so that's going to be an aldehyde. Over here, double bonded oxygen to a middle carbon, so there we have a ketone. Last one we're looking at is going to be your double bonded oxygen and a hydroxyl group on there. So there's your carboxylic acid. All right, hopefully you're feeling pretty adept with all that. And that is it. So you guys get to work on some homework problems.